Hello, good morning, good afternoon, and good evening, anybody. Welcome to today's webinar on how cutting-edge cell technology can help module manufacturers outperform the competition. My name is Casey, and I'm a section editor at PV Tech, one of the publications of Solar Media. And today we're going to be discussing this very topic. As I'm sure we're no doubt aware, as global solar installations continue to grow rapidly and there's more interest than ever before in the sector, and solar power continues to grow for a greater account of the world's energy mix, there is a greater demand than ever for high-efficiency solar cells. Cell manufacturer Jiatai Solar is a leader in this regard, boasting 40 gigawatts of annual N-type production capacity as of the end of 2023, and has completed shipments of N-type products of more than 19 gigawatts in the first half of this year. Today, JTPV Research and Development Manager Jinrui An will discuss how cutting-edge cell technology can help module manufacturers outperform the competition, and what steps the company has taken to drive progress in this area. We'll hand over to the presentation in a second. If you have questions, you're welcome to leave them in the Q&A box below, and we'll get to those for which we have time at the end of the presentation. So without further ado, Jinrui, over to you.
Thanks, Casey. Good afternoon, everyone. I'm Jinrui from JTPV. It's a great honor for me to share our cutting-edge cell technologies here today. And we believe they can be very useful for module suppliers to outperform the competition during this tough period of time. As a professional cell manufacturer, our goals are to empower customers with technological innovation and maximize power generation from improved cell structures. In this report, we'll highlight the technologies embedded in our latest half-cell product, Mono 2, including advanced metallization, improved edge passivation, and rear optical optimization. For those who are not familiar with JTPV yet, our standard product, Mono 1, is an N-type cell that comes in a variety of 4 wafer sizes. It involves a range of techniques such as a stack wafer depot process, emitter metal contact optimization, super thin fingers, and super multi-bus bar. Due to the time limit, I will only cover these technologies very briefly today. The stack wafer depot process is basically to put a pair of wafers back to back or face to face, depending on which side you want to process. There will be a slight wraparound on the other side, which can then be removed with a single-side wet chemical process. This technique can be applied for all the thermal processes and double our production capacity compared to standard double-side processing. And we must also carefully control process parameters such as the ramp-up rate and certain gas flow, because the wafers will have thermal stress due to asymmetric deposition of fumes. The emitter metal contact optimization allows us to use less corrosive silver paste to reduce the amount of silver and aluminum spikes for lower contact recombination. It can lead to about 5 millivolt increase in VOC without significantly impacting contact resistance, leading to about 23% absolute efficiency gain on the cell level. The super thin fingers and super multi-bus bars are both improved metallization techniques that can facilitate thinner fingers or bus bars respectively. And we can decrease the grid spacing so that fill factor can be greatly enhanced. For module suppliers, the use of super multi-bus bar can also reduce resistive losses for the modules and therefore increase CTM. Now let's move to the 3 new technologies I want to discuss in detail today. First is the Super Thin Finger Plus. With the development of silver paste to enable increasingly thinner fingers, cell manufacturers can routinely print fingers under 20 microns wide. In JTPV, we have developed a novel fine-line printing technique, branded as the Super Thin Finger Plus, to further push the limit down to 15 microns. Narrow fingers with smaller spacing can lead to reduced resistive losses in the metal grade and in the emitter as well. It also can reduce shading for the cell, allow for higher emitter sheet resistance to increase cell VOC, which can potentially lead to better CTM for module suppliers. This slide shows some of our cell results. Note that we've conducted numerous experiments with different combinations of masks and silver paste. And the mask and silver paste used here is 100% relevant for mass production. As you can see, with VOC and GSC roughly unchanged, fill factor increase leads to about 0.1% efficiency gain. This is primarily due to the improved finger aspect ratio from about 55 to 70%. And in the experiment group here, we simply increased the number of fingers by about 10%. Potentially, we can also adjust emitter sheet resistance to shift toward higher VOC rather than higher fill factor with the same efficiency gain of 0.1%. And this can lead to higher CTM for module supplies. Better finger aspect ratio also makes possible the trade-off between cell efficiency and silver consumption. For instance, we may opt for lower silver usage while maintaining the same efficiency as the baseline group in times of high silver price. It is easily achievable by adjusting the screen printing settings. And this strategy also leads to better cost effectiveness for our products. And the second feature of Mono 2 is the so-called half-cut edge passivation. Nowadays, mainstream module suppliers usually prefer half-cut cells for reduced resistive losses in the modules, leading to about 3% increase in power output. This has been kind of standard approach since PERC time. However, as the cell VOC increases, the influence of laser cutting on cell performance is becoming more obvious. Laser cutting may introduce silicon dangling bonds and other defects at the cell edges, resulting in increased recombination of electron hole pairs, and this can lead to decreased minority carrier lifetime and increases the risk for microcracks. Generally, cell efficiency can be reduced by more than 0.2%, with the most impacted parameter being fill factor, as you can see in the table. And note that this is the case even with the so-called damage-free laser cutting, because the cut surface is devoid of any passivation layers. In JTPV, we developed an edge passivation process for half-cut cells. After laser cutting, we stack the half cells together in hundreds or even in thousands to deposit a thin layer of passivation film, such as aluminum oxide or silicon nitride on the laser edge. We can then perform an extra test and sort step to group the half cells according to their S-passivated characteristics. HEP primarily increases cell fill factor for all the cells, but there may be outliers whose GSA or VOC are also impacted somehow. So this extra test and sort step is highly recommended. From the SOUNS VOC results on the bottom left, we can find that the pseudo fill factor is increased by 0.8%, corresponding to about 0.2% in efficiency. This is in good alignment with the final IV result on the bottom right. Just like the reverse process to laser cutting, the cell efficiency is almost fully recovered. In a recent experiment, which is not shown here, we noticed that the thermal process itself during film deposition can also improve the surface and the bulk passivation, but the underlying physics is still under investigation. This demonstrates that there may be still room for power increase with HEP process. And this slide shows some module results. An increase of 5 volts is found with both single glass and double glass modules, as discussed earlier. Performing an extra test and sort step may further increase the power of modules, with the best beams because of more concentrated cell characteristics. And counterintuitively, cutting into halves can also slightly improve the yield, because roughly 40% of EL problems only occur in one half of the pair. So in this case, cell manufacturers don't have to downgrade the good half cells. And lastly, wraparound of passivation films only covers very marginal area on the cell edges and does not pose a problem for cell welding or aesthetics for the modules. Another feature of Mono 2 is improved rear optics. From an end user's point of view, diverse application scenarios demand power generation using all possible sources, including the albedo. Therefore, it is important to reduce parasitic absorption by optimizing the properties of the rear layers. By modulating layer thickness between rear fingers to form an optically inhomogeneous structure, we have improved the cell characteristics and achieved bifaciality up to 90% on the cell level. And we term this technology as the wave back surface field, or WBSF in short. And this slide shows the cell results for WBSF. An increase up to 0.15% in cell efficiency is achievable with a boost in GSC that overcompensates fill factor loss due to the increased rear sheet resistance. Note that for WBSF technology, we have a relatively wide range for parameters. For example, we can change rear passivation schemes and also the percentage of area that receive the treatment. The higher the percentage of treatment, the larger the efficiency gain is. But in real production, we must balance efficiency with yield and throughput, and 50% will be a sweet spot. With the use of WBSF, cell bifaciality can be increased by about 6%, as you can see from the table. WBSF technology greatly broadens our application scenarios. In cases of large solar farms with adequate ground reflection, or certain distributed applications like carports. The high bifaciality of Mono 2 can bring about extra power. We've also tested different background materials, including white paint, sand, concrete, grass, and water, and found up to 20% extra power can be generated from the back with our Mono 2 cells. As a professional cell manufacturer, we have the capacity for all the common wafer sizes. And this slide summarizes our standard cell products, including 182, 210R, and 210N, with their corresponding module power. A gap of about 10 watts between Mono 1 and Mono 2 on average results from the three technologies we just covered. And notably, bifaciality on both cell and module levels are significantly improved with Mono 2, making them uniquely competitive for bifacial applications. Compared to standard P-type PERC, N-type modules have higher bifaciality, up 85%, and this can lead to 1 to 1.5% extra power. And N-type modules also have better performance thanks to their lower temperature coefficient and working temperatures than P-type PERC, leading to about 2% power gain. Moreover, free from light-induced degradation, N-type modules also feature lower first-year and annual degradation than PERC, corresponding to about 1.8% power gain with an extra 5-year module lifetime. In summary, N-type modules have the strength of being LID-free, good PID resistance, lower encapsulation loss, lower temperature coefficient, better weak light performance, and consequently, higher power output than standard PERC. This slide shows some generation gains and losses caused by impacts of temperature, degradation, and bifaciality, with PERC being the benchmark. We can see that Mono 2 has superior degradation and bifacial properties even than Mono 1 and has about 1% advantage in BOS cost and LCOE. 210 modules are slightly more cost-effective than 182 modules due to their larger size. Please note that this data is based on the simulation of a 10 megawatt site in Qinghai province, China, that has a dry and cold climate with good insulation, ideal for PV applications. For most other locations, the difference between Mono 2 and less advanced module types may be even greater. Reliability indicators for N-type modules are usually well below the IEC standard of 5%. Our Mono 1 and Mono 2 products show even improved behaviors, especially with DH1000 further reduced to below 3% of single glass modules. And this result can be very promising for the distributed market, where single glass modules dominate. This slide shows some of our qualifications from both CNAS and TOV-SAT. And we also summarize the range of tests we can perform, including LETID, water boil, acetic acid, DH on the cell level, and DH, HAST, TC, etc. For modules. In summary, Mono 2 can help customers to maximize return on investment with efficiency, reliability, as well as sustainability. It not only enhances individual module output, but also reduces the overall performance and BOS costs, especially in the case of bifacial applications. In terms of reliability, taking advantage of its superb DH performance, Mono 2 is well suited for high temperature and high humidity environments with minimized degradation and ensuring stable power output within its lifespan. Finally, using Mono 2 can also ensure you to partner with the global leader in N-type PV technology to maintain your technological advancement in future. Speaking of technological advancement, this slide shows our latest cell result certified at ISFH with efficiency exceeding 26%. This cell exhibits extremely high VOC over 743 millivolts with excellent surface passivation. And we also struck a perfect balance between JSC and fill factor with carefully tuned super thin finger pass and WBSF recipes. Note that this cell is just the 182 full cell and didn't receive any HEP process. We believe had we cut it into half and treated it with HEP, it would even have a higher efficiency. And notably, all the processes here are based on industrial equipment and materials, only with very minor modifications, such as the rear WBSF percentage just mentioned, demonstrating that our Mono 2 cells have the potential for even higher efficiencies. And finally, some background information about our company, JTPV. We are a professional N-type solar cell manufacturer that operates 2 production bases totaling 40 gigawatt in Chuzhou and Huai'an, China. We've been taking the lead in N-type solar cell shipment since Q2 last year. And in the first 3 quarters of 2024, this year, we made a total shipment of 26.4 gigawatt, among which over 90% are N-type. Originating from China, JTPV aspires to global leadership, with overseas sales team across Europe, Middle East, and North and South America to cover all the important markets. Earlier this year, we've also started the construction of 5 gigawatt cell production facilities in Oman. And we are among the first Chinese companies to set up production bases in the Middle East. This slide shows our awards on different levels, including industrial, provincial, and national, as well as some of our partners and clients. As you can see, a great number of them are actually overseas companies. And finally, here are some ESG stats. Cumulatively, JTPV has made over 80 gigawatt cell shipment and been an active player toward China's 30/60 decarbonization goal. That's all of my presentation today. Thanks for your attention.
Thank you, Junrui, for that presentation and that insightful look at the Mono series in particular, and also discussing some of your point there at the end about China's decarbonization goals more broadly, just because I'd like to ask some follow-up questions based on that. And one of them does focus on some of the global, more macro challenges for the renewable sector, for the solar sector as a whole. How does the Mono 2 series help to address challenges such as the need to ensure cost reduction and deliver efficiency improvement in the global solar sector?
Mono 2 cells help us to reduce manufacturing costs by optimizing production processes. For instance, we can make trade-offs between performance and cost. As mentioned earlier, with the super thin finger plus technology, we can choose between the 0.1% efficiency gain or the savings on silver cost. And this allows us to be more flexible and increases our adaptability to different customer needs. And for efficiency improvement, the certified result at ISFH demonstrates very high efficiency and VOC. And importantly, it is based solely on industrial relevant processes, only with very minor modifications, showing that the potential for our Mono 2 products.
I think one of the questions that's often asked in the solar sector is, okay, how does this affect actors across the sector, from upstream to downstream, the whole range of it? What are some of the key benefits of the Mono 2 series for EPC companies and end users in particular?
For EPC companies, Mono 2s can help to reduce the BOS cost by increasing power output per module and also the electricity generation per watt. This can greatly thin down the fixed costs such as land and infrastructure. And end users can benefit from the improved return on investment through higher energy yields and lower long-term maintenance costs.
And I think delivering that efficiency, especially from, say, a land use perspective, is very important because solar projects are here to deliver renewable power. How does this series help to support global sustainability goals for global energy projects?
Mono 2 reduces energy and material such as silver consumption and enhances module efficiency, so it can minimize the carbon footprint of production. Its long-term reliability aligns with the global ESG goals, making it a sustainable choice for large-scale projects. And moreover, Mono 2 has a very high bifaciality, making it ideal for bifacial applications and bringing actual benefits for its end users.
And sort of you've talked a lot about the global nature of geoscience solar in particular, and the various sort of sectors that you're active in. What about some emerging markets like India and Turkey? How can the Mono 2 series help businesses gain a competitive edge in those kind of environments?
In our opinion, markets like Turkey or India are very important. They have the unique strengths of being friendly to novel technologies, and these markets are keen on high-performance products. So we believe that Mono 2 is well suited for these high-growth markets, and it can enable businesses to meet local energy needs while maintaining global competitiveness.
Which I think is often a good balance between those two kind of aspects of things. From a financial perspective, how does the Mono 2 series improve project financing opportunities for developers? Because ultimately, if someone's going to invest in this kind of technology, it needs to be financially viable to do so.
The technology of Mono 2 its high efficiency and reliability can lower the project risks and make it more attractive for investors. For instance, it is free of LID and it can exhibit very good PID and DH performance, guaranteeing very low field degradation. As a result, developers using Mono 2 can achieve better financing terms and faster approvals for green energy projects.
There have been a number of questions about some of the future of the Mono 2 series and your approach in that regard. In general terms, what future upgrades, updates, innovations can we expect from the Mono 2 technology?
The three technologies we introduced today still have room for improvement. For example, with the super thin finger plus, we can now print 15 micron wide fingers, right? But this is definitely not the end. We are already working on reducing it to 12 microns and beyond. And the same story with HEP and WBSF, where we're looking into how to not only increase cell efficiency, but also simplify the process. So in short, we'll be expecting cell products with even better performance at lower cost in the very near future.
And I think that there's a question here talking about the aspect ratio and of some of the fingers used in cells. Does it mean that cell orientation, not just the sort of structure, but how they're aligned, how is that particularly important for a technology like this, but also for product design in general?
Yeah, I think there's a general trend for the metallization to go to very tall and thin fingers, and this not only depend on the mask and paste companies, but also our cell manufacturers as well, because we have to integrate all these materials and make a stable and high efficient process, so that we can limit the shading on the cell while having a good fill factor for the cells.
That certainly makes sense. There's another question here from one of the members of the audience looking at a sales plan ahead, asking when the half-cut cell will be available in the market. Do you have any kind of time frame looking ahead from a sales angle?
Actually, we're already running pilot line for these HEP cells, and but if you want to order large quantity, maybe you have to wait till the start of next year, I guess. Mm-hmm. But basically, we just put adding a few equipment at the end of our current production line, which in my opinion won't take much time. So it's not a very difficult issue.
Which is good to hear, not just for our work here in particular, but the renewable energy transition in general, right? Anytime we can accelerate these processes quickly is a good idea. I also wanted to point out, just because it often comes up, this presentation will be recorded and made available later, so this can be shared around once we're done here. Just looking over some of the other questions. Some of the questions that have been asked, our colleagues have said to reach out to us via email, so we'll be able to pick up your questions in greater depth there, just because we don't have all the time in the world here today, and we want to make sure that some of these questions can be answered fully rather than sort of just quickly right now. Jinrui, was there anything else that you wanted to bring up about the Mono series and about some of the topics that you've talked about today?
That's pretty much it.
Cool. Well, great. Thank you. I mean, that answers that. Those of you that have more questions that need to be answered, please do let us know. You'll be able to submit your questions via email. We'll get back to you. Until then, thank you, Jinrui, for your time. Thank you for those of you who were in attendance. And we'll see you next time we work together on a webinar.